Right. Hello, everyone. Yes, my name is Robin Ramstad. I'm a postdoc at the University of Colorado, Boulder. And most of this work and the thought behind it ties back to work that I did with my PhD supervisor, Dr. Stas Barabash. And I'm here to answer the burning question: do intrinsic magnetic fields protect planetary atmospheres from stellar winds? And if you're familiar with Betteridge's law, then maybe you figure that I've already spoiled the title of my the conclusion to my talk, because any headline that ends in a question can be answered by the word no. But as I'm about to show you, it's a bit more complicated than that. So take two planets, one with a global dipole, one without a global dipole, and the general picture that you might have is that the global dipole, yes, it stands off the stellar wind at a great distance, and so it protects the planetary atmosphere from interacting with the stellar wind. Whereas without the global dipole, you get this much closer interaction, and so more atmosphere should be stripped off by the stellar winds. So if I pretend to be an exoplanetary scientist, and I find my hypothetical star system, which features a middle-aged main sequence G-type star surrounded by at least 3 terrestrial planets, and I find that the innermost planet has about 100 bars of atmosphere, and then they drop off to 1 bar as you go further out, and 0.01 bar further out than that. Now, I might be perplexed because the innermost planet gets subjected to the strongest stellar winds and the strongest ultraviolet radiation from the star. So what's going on? Well, maybe, because I know of this theory, maybe I figured that this planet is getting protected by some strong magnetic field that is shielding it from the stellar winds. And so I can start to speculate how about the core composition, the amount of metals in there, et cetera, until I look really close and I realize that's actually our solar system, that's Venus. And we know that it doesn't have an intrinsic magnetic field, it's Earth that does, and Earth has less of an atmosphere. So now I become a planetary space physicist, and I realize I can probably help here. And I still realize that, well, probably if I was an exoplanetary scientist, what I would need is some model that where I can plug in the planetary properties like gravity, magnetization, atmospheric composition, and mass, as well as stellar wind properties, energy inputs from EUV, and so on. And from that, get some escape rate that I can integrate over time to find how much atmosphere has been lost from my planet. And so in the solar system, I have a nice laboratory with 3 planets at least that share some features and differ in others. So if I compare Earth and Venus, well, they have similar gravity, but they have different magnetic fields. Earth has a global dipole, Venus does not. And Venus and Mars, neither of them is magnetized, but they have different gravity. So that tells me something about the effects of gravity while constraining the other properties. And fortunately, around all these planets, we have had orbiters for many, many years that have taken measurements. Around the Earth, there's the cluster mission, for example. There's Venus Express around Venus, and there's Mars Express and MAVEN around Mars. I would love to include also Titan and Pluto and perhaps other bodies in the solar system, but unfortunately there are no orbiters, and you really need a lot of data to do the kind of analysis I'm about to show you. And I'm also interested in getting such a model for the ion escape rate, because as a planetary scientist, I'm interested to find out how much atmosphere has been lost from the planets in the solar system themselves. The sun has changed over time. About 4 billion years ago, the solar wind dynamic pressure was 2 orders of magnitude higher than it is today, and the amount of photoionizing flux, EV flux, if you will, was about an order of magnitude. And today, well, there's still some variation because of the solar cycle and stochastical solar activity that allows me to get conditions that are representative of nominal conditions about 1 billion years ago. But that's it. So if I want to go further back in time, I need to model the dependence in this available parameter space. This is over 10 years of Mars Express observations, and then extrapolate my escape rate back 4 billion years. And escape from the different planets work kind of different because they have different gravity. So for a particle to escape from Earth to Venus requires about twice the velocity of that of Mars. which in terms of energy means that a particle requires 4 times the energy, even 5 for Earth compared to Mars. A hydrogen particle, well, it doesn't really care that much, because in either case, the particle is going to escape thermally from each of the planet, or at least it's neutral by some collisional process. However, oxygen, atomic and molecular oxygen, is a different story. Here you require amounts of energies for Earth and Venus at least that is not available through any neutral escape process, maybe with the exception of sputtering. But there is another energy source required either way, and one such source is the solar wind. And the solar wind will induce electric fields that it interacts with the magnetosphere or any kind of object in the solar system. The electric fields follow from the generalized Ohm's law that Dave mentioned earlier, where you have a motional component, a Hall component, and an ambipolar component. And the ambipolar component in the case of the Earth will channel out the ions from the polar regions, from the auroral cusps in the polar regions into the magnetosphere, where they can take any of the number of paths. They can end up in the plasmasphere, they will get trapped for a while and then maybe return, or they will diffuse out into the magnetosphere and then into the solar wind, where they get picked up by this motional electric field. Or they might end up in the plasma sheet, where they get accelerated further downstream by this current J in the whole term, or they get accelerated back towards the planet and end up trapped in the ring current, contributing to it before they diffuse out and again get picked up. Or they simply escape right down tail into the lobe, one of the magnetic lobes. In the case of Mars, the solar wind is magnetized, so it encounters this conductive obstacle, and you get similar kind of forces. There's an ambipolar electric field that pulls ions into the night side, where they can get accelerated by plasma sheet acceleration in a similar mechanism, or they can get pulled out into the solar wind and get picked up by this motional electric field, which is really energetic. And the solar wind is staved off because you have currents here in the upper atmosphere, which enhances the magnetic field that in turn deflects the solar wind around the planet. This is not a direct collisional interaction. This is an electromagnetic interaction, an induction process. And when space physicists talk about these currents, they usually count on the audience to fill in the blanks, to make a mental picture for them, because they don't really know what the currents look like. Until very recently with MAVEN, we managed to find out, we mapped out the currents quite recently, and we can see these currents in the ionosphere that then connect to the opposite currents in the solar wind. And this is what connects or couples the two regions together. And if you want to read more about this, then I suggest you look for a Nature Astronomy paper that is about to appear reasonably soon. In order for an escape to occur, you need two things. You need energy and you need to create the ions. There's only about a million times less ions as there are neutrals. And the energy will come in the form of electromagnetic energy flux or Poynting flux, if you remember your E&M terms. This can be direct current Poynting flux or alternating current Poynting flux, so waves. And you need to produce the ions, right? So ultraviolet photons, they don't care about magnetic fields. They go straight into the neutral atmosphere where they ionize, create ions. And those ions then have to diffuse upwards into the region where the energy from the solar wind is getting deposited. This is in the case of an induced magnetosphere, but for an intrinsic magnetosphere, you can imagine the field lines being vertical instead. And so then the energized ions escape to the night side either way, or out into the solar wind. But either way, these two flows, energy and particles, have to meet somehow together, and either one can limit the total escape rate. With MAVEN, we can measure the ions directly. This is from an instrument called STATIC that measures the direction of ions, it measures the energy, it measures their mass, and so you get spectrograms that look like this, with as the spacecraft flies through different regions of the planetary environment. You have protons, you have oxygen, you have molecular oxygen getting accelerated to very, very high energies. This is escape energy here in these dashed lines. But they only start to make intuitive sense when you map them out in space. So, and this is showing you measurements at the Earth, at Mars, and at Venus, plotted to the same scale. And this tells you how important it is to map these fluxes out in space. You can see that this is the line where the solar wind interacts with the planet, the dashed line over here. And so you see that the magnetic field, yes, it holds off the solar wind at a great distance, but it increases the interaction area by the square of that distance. And so you get about 100 times more energy available to interact with the magnetosphere, energy that can be channeled into the ionosphere if coupled with the ionosphere. And so how does this influence escape? Well, let's look at the measurements. We can make these maps and integrate them over area for all the different planets. And this has been done by a number of studies, and I'm showing you 3 of them here. This is quite recent work in all of them. And you can see Venus, this is all showing you escape rates on the same scale of dynamic pressure. And you can see that Venus, yes, it increases a little bit. The escape rate increases a little bit as you increase the dynamic pressure. But compare it to the Earth. This is 2 orders of magnitude over the span of the parameter range. And if I compare Earth to Venus, I can pick this data point, or I can pick that data point, and I can say that the magnetic field is either protecting the atmosphere, it's about several factors lower, or it's exacerbating escape by increasing it by an order of magnitude. But as you can see, when you look at different dynamic pressures, the different upstream conditions, it really depends. And also you can see a difference. Yes, Venus is increasing, Venus escape rate increases with dynamic pressure. Mars, not so much. It seems to not be that sensitive, or maybe even decreasing a little bit. So the question is, what is going on? What is the common picture between all of these? And there's also a difference in the influence from EUV. You see that EUV is increasing escape from Earth and from Mars, but not so much for Venus. It actually decreases at Venus. And it gets more evident when you start to look at when you plot the escape rates versus EUV or photoionizing flux. At Mars, there's a linear function, more or less, whereas at Venus, the escape rates indeed tapers off. And that's the reason that it tapers off is because the return flux is increased. So as you increase the amount of EUV flux, more and more ions start to return to the planet. This is related to the coupling that occurs in an induced magnetosphere. As you increase the EUV, the coupling coefficient, the coupling efficiency goes down. So less and less energy is getting transferred into the ionosphere. Whereas in an intrinsic magnetosphere like the Earth, the coupling actually goes up. This is showing you currents that connect the magnetosphere to the ionosphere as a function of an EUV proxy. And you see that as the EUV increases, these currents go up for the same upstream conditions. The dependence with solar wind is also quite evident. You have, when you plot the coupling coefficient as a function of dynamic pressure, you see that the coupling goes down in an induced magnetosphere like Mars or Venus as the dynamic pressure increases. So there's a decrease in the return in your ROA effectively for an induced magnetosphere, whereas in an intrinsic magnetosphere, this coupling for most of the parameter space is pretty flat and mostly varies stochastically with, say, upstream IMF orientation, interplanetary magnetic field. And so put this all in the same framework, it seems that Mars, under its typical conditions, is in a supply-limited domain. And in this domain, if you look at the escape rate shown in color, if you increase the ion supply rate, your EUV, then you do 2 things. You change the ion supply, but you also change the powered rate by decreasing the coupling. So this position of the planet, the typical position, as you increase the EUV, it decreases coupling, but that doesn't matter for the escape rate in the supply-limited domain. Rather, the escape rate increases because the ion supply increases. And oppositely, if you increase the solar wind, yes, you increase the power rates, but that doesn't really do much. in this domain. Venus is the opposite. Because it's in an energy-limited domain, you increase solar wind, escape rate goes up. But again, it's a decreasing return of investment because of the decreasing coupling with solar wind. And when you increase EUV, coupling goes down, so escape rate goes down. Earth is extremely sensitive to both solar wind and EUV, and so escape rate goes up dramatically as you increase either solar wind or EUV. Comets have almost no escape energy required, so as with very low gravity, this term is almost zero, and equivalent power rate is always going to be at its maximum. It's always going to be in a supply-limited domain. I see I'm out of time, so I'm going to leave my conclusions up and simply move to the last one to answer the first slides in my talk. Venus may actually have retained its atmosphere not despite having a global dipole, but given the evidence in the solar system, maybe because it lacks a dipole. Thank you.